Well, normally I would comment about half the class being out, but I'm pretty sure half the class is out sick. There's something pretty nasty going around.
Well, sick or not able to get it out of the machine at the moment.
Oh, yeah, because of the bomb threat.
Yep.
Yeah, that's,
I just leave early, but I'm pretty sure that's blocking off the exit.
wow.
Yeah, like I left sometime around, I wanna say like literally 8 on the dot. And I got that about after walking into the tablet.
Wow. Wow. Yeah, obviously can't blame anyone for that. So we're gonna do our best to make this very productive. Happy 8th week, by the way. I'm sure everyone's very excited about that. So. Announcement. I'm not quite sure what I want to do about this. My best plan at the moment is just kind of to stick with how things are, but I will let myself be influenced by anyone's decisions here. So the material that the 8th covers is both the current assignment due Wednesday and the assignment that I revealed that is due next Wednesday. The recursion questions on assignment 4 are again pulled directly from historic lakes. So my recommendation, especially given that we're just starting recursion implementation today, is that we're a little bit behind on that, and it would be good to get practice with that. So if recursion is not something that you are super familiar with, my recommendation is to get started on that, get stuck on that, and come see me for assistance. If that means that you need to prioritize that over the current assignment, if I can see you making progress on the other assignments, then I would be okay pushing back the other assignment for you, probably specifically, so that you can have the time and space in your schedule to focus on recursion. I feel like recursion is more of a weakness than sorting. And the little bits of inheritance that are involved in that. It's not really inheritance, it's more polymorphism. But I don't know, people's thoughts on that. How do we feel as a class about both of those? Where do we want focus to be? And I don't want to spend too much time because I want to get implementing. But if you're concerned about that, if you're concerned about wanting to get more experience with recursion and focus on the recursion assignment, I guess talk to me and we can come up with a schedule to get both of the next couple assignments in over the next 2 weeks, but I can restructure things a little bit for you to make sure you're prioritizing, or you can prioritize both being successful in this class and prioritizing the age at the same time, given your current strengths and weaknesses. All right, we got to get started implementing because we have a lot of recursion to implement for the next couple of days. So we've gone over what it is, how to think about it. We introduced the concept of the factorial last time. So we're just going to get started implementing. And we're going to start with these first couple. We're going to implement them both in an iterative way and a recursive way. Okay, so we're going to start with an iterative factorial. I'm going to call this factorial iterative. Just to give it a terribly long name. It's going to take an integer and it's going to return an integer. So it takes something like 5 factorial returns 5 times 4 times 3 times 2 times 1, 120. So it takes an integer, returns an integer. How could we do this nice and easily iterative? So using a loop. We know n is passed in. What's the easiest way to do it? Some kind of for loop? Anything we need to do before we get into the for loop? Yeah.
Create a variable of the total.
Yeah, we need some kind of product variable. So we're gonna start out a product. What should we start the product out at? 1. Very tempting to put 0 here like you would with a sum. If you put 0 for a product and then start to multiply it with things, it's not gonna go so well. 0 times anything is still 0. So if you have a product variable and you find that no matter what you do, the answer is always 0, it's probably because you started your product variable out at 0. Then we can go into a loop that says, for, we're gonna use some counting variable. Where do we want to start that counting variable out at? That is one possibility. You can start at 1 and count up to n. Typically, when we write out a factorial, we start out at the higher value. We say something like 5 factorial is 5 times 4 times 3 times 2 times 1. So to make this similar to how we're going to handle the recursive version, we're going to start out at the higher end as well, but there's nothing wrong with starting at a lower value. So it's not wrong. What is that high value? Correct. N. We pass in n, we pass in 5, wanting to calculate 5 factorial, so we're going to start out at n. We're going to continue as long as I is greater than or equal to 1. It's kind of a waste to do this when it's 1. Multiplying something by 1 is just itself. So if you did greater than 1, it's probably better, but just because we state that 1 factorial is 1, and we say that 5 factorial is 5 times 4 times 3 times 2 times 1, we're actually going to go through and do the times 1, because again, I want to be able to link this to our recursive version that we do later. So it's a slight amount of wasted work now, there's a reason for it. We'll come back to how this relates to the recursive version here momentarily. So here's our loop. We're starting at the high end, moving toward the low end. And then each pass through, what are we doing?
Multiplying the product by whatever I is.
Yeah, multiplying the product by I. And we say product times equals I. Perfect. So once we're done with, this is the only thing we need to do in our loop, right? Everything else is handled by the for loop logic. We're gonna decrement I each pass through. Once we're done, we're ready to just return. Where's the answer stored? Product. So we can test this. Let's write a quick main instead of having an actual driver. So we will print out something like great. Let's check and make sure that we are in fact getting 120, which we are. Good. This works. Any questions about the iterative version of factorial with a loop? Yeah.
Why do we have greater than
Yeah, so here we're starting I out at the value of n that we pass in. So in this example, I passed in 5. And then this is decrementing each pass of the loop. So it starts out as 5. And then when we loop back around, I is now 4. So we're taking product. We start out at product as 1 times 5. That's 5. Next pass through, multiply that by 4. Next pass through, decrement I times 3. Next pass through, decrement I to 2, multiply it by 2. Next pass through, this is the wasted one. We're multiplying it by 1. But it links to something in the recursive version, so I keep it there just so that we can look at what's happening in the iterative version versus the recursive version. But yeah, we're decrementing I here, so and getting down to 1, because if we wrote out the expression, we would have 5 times 4 times 3 times 2 times 1 as optional. Question? All right, now for the new stuff. Let's actually think about how do we do this recursively. So we are basically going to copy the entirety of this because it stays exactly the same. What changes when we want to do this recursively? So we talked about recursion as a way of saying, okay, now we're in something like a line. And this metaphor can take us through a lot of different kinds of recursive problems. So we're in line and we want to calculate 5 factorial. For some reason, and for some reason, the people in line are going to be able to help us with this. But our task is to calculate 5 factorial. We know that we can break down 5 factorial into 5 times 4 factorial. We know it's 5 times something, and that something can be said as 4 factorial. So our task is to do that breakdown. We have 5 and we have 4 factorial. We're going to pass the 4 factorial on to someone else, saying, solve this problem for us. When you return to me with an answer, I'm going to multiply it by 5, and that's going to be the answer for 5 factorial, because an equivalent expression for this is 5 times 4 factorial. So this is this the base case or the recursive case? We talked about each one of these. Recursive case, yeah, it's the general case. The base case is when we already know the answer. For 5 factorial, we don't already know the answer. If we knew the answer, we would just return the answer. But since we can break it down further into 4 factorial, it's going to be the recursive case. So something is going to go before this that says, if we're in the base case, handle the base case. But starting to think about this from the 5 factorial case, you can think about this really either way. But the way we're going to return from this is we're going to say, okay, we want to return, what is the expression now in terms of something in code? We said it's 5 times 4 factorial. Translating that to what to write here. Where is the 5 coming from? Yeah.
So it would be return n times factorial recursive n minus 1.
Yeah. That is perfect. Does this make sense as a line? Can anyone explain exactly what this line is doing? If not, I'm happy to. Let's go here, yeah.
So it's just taking the value of n that was originally passed in and multiplying it by basically calling the function again, but with n minus 1, so it'd be like 4.
Yeah, so the current value of n minus 1 is 4. This is going to make a new instance of factorial recursive, where the new value of n is the current value of n minus 1. Notice how this process doesn't stop. It's like a loop without a termination condition. So this would continue and continue and continue and continue. Nothing says we're going to stop when n is 1, or n is 0, or n is negative a million. Doesn't matter, we're not going to be stopping. So how do we stop? We have to identify the base case. Where is a value of a factorial where we know the answer off the top of our heads? Yeah.
Wouldn't that be like 1?
1 would be a great way to start. So we could say something like, I don't need this many lines. We could say if n is equal to 1, return 1. This creates one slight issue, but it doesn't create it. It's still there. Can anyone identify the edge case issue? Yeah?
N equals 0.
Yeah, if we query what is 0 factorial, we're going to spin infinitely because we have no way to terminate this. So the way we're going to get about this is we're not going to specify that this should work for anything that is negative. So we're going to say if n is 0 or n is 1, then we should return 1, because 0 factorial is also 1 by definition. We could also throw an exception in here. I'm not going to go through the logic of if the user passes in something negative, we should throw an exception. If we were making this production code, we should absolutely do that. But for the purpose of illustrating something that is recursive, I don't find a ton of value in that. This is it. This is done. There's nothing more to be done here. So to test this out, we will just do exactly the same thing. Copy the exact same line and now say that the recursive version of this is going to be factorial recursive. Make sure we call the right one. And we see that in fact, they give us the same answer. Questions about how the recursive version works? I can draw out exactly what's happening in more detail, probably should. Let's actually go through it with a slightly smaller example. I'm going to do this with 3 factorial, because 3 factorial is a little bit smaller and a little bit better. Off the top of our head, so 3 factorial, just to ground this, 6. So the answer that we should get from this is 6. So recursive functions look and feel like they're something that is, the first time you see them, very different or very. But they're not. It's really just calling the same function multiple times. So you can think about what's happening is pausing one instance of this and then starting another one. So what I'm going to do is I'm going to start with this code and then I'm going to start drawing some adjacent instances of this to talk about where we are in this process. So we call factorial recursive. We're going to come in here and we pass in, that is a terrible arrow. I'm going to pass in 3 and say, great, n is 3. So is n 0 or 1? No, we're going to come back to this point and note that we're not ready to return. We need to resolve what this factorial recursive n-1 is before we do that. This is the equivalent of we don't have enough information to turn around to the person behind us and reveal an answer. We have to ask forward. So we are going to do that. We're going to remember that we are on line 17. We're pausing this instance of this method. And we are now going to make a new instance of this method. So everything that is right here, we are going to duplicate and is now right here. So exactly all of these lines is now in another instance of factorial recursive, where what's being passed in is 2. Is n 0 or 1? No, it is 2. So we move past the if and we move to the return. But unfortunately, we can't evaluate this factorial recursive yet. So we're going to put a pause on this function at line 17, and we're going to duplicate. We're going to make another instance of this same method, and coming in is n equals 1. Now, is n 0 or 1? Yes. So we can just straight up return 1. So the factorial recursive in this line 17 is 1. That's what this is doing. This is resolving and returning 1, which removes it completely from what we're going to call the call stack. I'll explain exactly what that is soon. This whole thing goes away. And now this factorial recursive has evaluated to 1. Now we're ready to evaluate this whole line. From this instance's perspective, what is the value of n? 2, right? We passed in 2. So n here is 2. We return n 2 times the value of factorial recursive, which is now returned. So we want to return 2 times 1. So this returns 2 to right here. Now this thing's work is done, so all of this goes away. We don't need it anymore. All we needed it for was this 2, and you can now see how this is exactly like this function turning around and communicating its answer, saying, hey, 2 factorial is 2. And now we have our answer so that we can now calculate 3 factorial as the current value of n, which to here was 3. 3 times 2, which is 6. And that's exactly how this returns the exact value that we need. Questions on any of that work? How this is exactly working? Yeah.
With factorial recursive use more memory than factorial degree?
It depends. So the call stack uses a different kind of memory and a different place than. Let's actually go over the call stack, because I think that is useful. The way that this is usually visualized in computer science is we have two different kinds of memory that work toward each other. On one hand, we have the stack moving down, and on the other hand, we have the heap moving up. The stack is where we store any local variables. So anything that we declare inside of a particular scope. So something like n in this function is a local variable to this method. That gets stored in the stack. What that means is whenever we change a scope, we can only see the variables that are in the stack for that particular stack frame. So when we make main here, there are no variables. You can imagine I made some kind of int x. Or even better, let's call it int n equals 3. Can we see this? I'm not going to use 3 because I just used 3. Let's call it 13 because 13 is very lucky or unlucky, depending on your perspective. Is this n visible from any other perspective? There's a different n with a different value, right? And that's legal because they're in different scopes. You can call variables the same thing as long as they're not in the same room. If I shout out the name of someone who's in this room and there's another person in with that name in the adjacent room, they can't hear me, so I can only be referring to you. There's no ambiguity, even though it's a common name, if there's only one of you. That said, there are so many Joshes in here that if I call out Josh, then half the class raises their hand, and that's okay too, but there's ambiguity because they're named the same thing within the same scope. So you have to further differentiate them. So this stack makes what's called a stack frame for every scope. So here might be the scope for main, and it's going to have a bunch of information about main. So it's going to have all of main's local variables. It's also going to have the current execution line number, so that if main gets paused for some reason, like say we call factorial iterative or factorial recursive, we know we have to come back to this at some point. So if we change the scope, how do we know to come back to this line? That's a piece of information that is stored in the stack frame for this function. But when we do call factorial recursive and pass in some value, it's going to make a new stack frame that's moving down. And we're going to switch to this is the now active stack frame. All the information that was here is still stored, it's just not active and accessible. So we can now duplicate the names of our variables. We can now reuse everything because it's a different scope. And this can continue. Now this is factorial recursive. But factorial recursive calls factorial recursive. Well, it's active. So factorial recursive now makes another factorial recursive. And this can continue arbitrarily long until something happens. The stack has a very limited amount of memory, and you will find that you can have about 40 or so of these active before you get what is called a stack overflow exception. And if you've wondered why the site that you go to answer so many questions is called Stack Overflow, this is where this comes from. So you get a stack overflow exception that says your stack memory has been exhausted. Your program must now crash because we cannot allocate more stack space for an additional call. And I will actually later on, not immediately, give you a way that you can work around this, but not in a language like Java because Java hates you. You use another type of language and you can actually use a more intelligent kind of recursion in a way that allows you to infinitely recurse without utilizing infinite stack space. So that's the stack. The heap keeps track of all allocated memory. So whenever you use the keyword new to make something, an array list, something that is a reference variable, The reference variable lives in the stack. But the actual data lives in the heap. So let's say we make a linked list. Singly linked list, list equals new singly linked list, and each of that, and this list is gonna have a bunch of nodes. And we eventually go through and make a singly linked list of a bunch of nodes. The actual singly linked list object is called list. And that points to an object that has, what did we say? It has a size, it has a head, and it has a tail. This concept. So this lives here, this lives here. So this is a local variable, this name for this structure, but the fact that this structure exists and can have multiple names lives in the heap. Similarly, when we make a node, the name for the node is a local variable and lives in the stack. The actual data of the node, its data, its previous, if it's a doubly linked node, and its next, are in the heap. That's probably as much detail as we need to go into to understand exactly what's happening. So to answer the question of does it use more memory, it uses more stack memory, but it might use less heap memory. And this can be okay as long as the size of each particular stack frame is small. That stack memory is very efficient and is there to be used. We'll find some examples. I will show you an example of when a recursive function is significantly more efficient than an iterative function that does exactly the same thing. But we'll start with the concept of anything you can write in a loop, you can write recursively, and vice versa. So it makes little sense the first time you see it as to why we care so much about recursion, but it ends up being a very powerful tool that has uses that are outside of the iterative uses. So that's my off the top of my head justification for why all of this is done the way it's done. Any further questions before we dive back into the next code? Yeah.
You mentioned something about the max number of stack things being something around like 40.
Yeah.
Does that mean you could call fractal recursive for a value greater than 40 for n?
Yeah.
Really?
You'll get a Stack Overflow exception.
All right.
And granted, more than about 40 factorial is a disgustingly large number that we can't store in things anyway, but for other kinds of recursive problems, you do have to think, I can't have a recursive depth of more than about 40. If you've designed a problem well, you shouldn't have a recursive depth of more than about 40. But if you start to see that Stack Overflow exception, that's usually what that's from. Actually, honestly, it's usually because you have an infinite recursion and some kind of infinite recursive bug. But questions on factorial before we dive into our next example? All right, the next one, and I might have people try to work on this a little bit. We're going to call this power of 2, and the goal of power of 2 is to determine whether a passed in value is precisely a power of 2 or not. How are we going to do this? So let's at least write out the method header. It's going to return us yes or no. It's either a power of 2 or it is not. And we're going to take in, well, something we're going to call, I guess, a query. Something that says, is this a power of 2 or not? So the first question I would have for you is, let's start the other way this time. What is the base case? Or maybe not. Maybe we start with what is the general algorithmic philosophy? I pass you in some number. How do you determine whether that is a power of 2? I would say whether it's even. And every power of 2 has to be even. But there has to be something further that we imagine now being in a line. How would you make use of a line of people for something like this. Utilizing the person in front of you. Yeah,
Repeatedly divide by two.
repeatedly divide by two, what would you expect to get when you repeatedly divide by two?
If it is, get down to just one.
Yeah, we get down to one, but every time we do it, the remainder of that division would be zero. So we need to use modular arithmetic to do it, but yeah, that's exactly right. So you are gonna have query. You are going to say, if I can evenly divide query by two, then I'm gonna pass on that number to the next person and say, is this number divisible by two? They're either gonna return back to me and say, yes, it was, or no, it wasn't, and not just that one number, but is that number a power of two? If that person's number was a power of two, then I am also a power of two, because I am 2 times that number. Therefore, I must also be a power of two. So our base case is just to say, basically, if the query is 1. It is a power of two. Beyond that, we just now have to answer a general case. How do we know the answer is false from our perspective? We said we were only going to pass on that information to the person ahead of us if what?
Query mod 2 is equal to.
Query mod 2 is 0. That says that it goes in evenly. So we could immediately back out and say it's not even worth bothering the person in front of us if query mod 2 is not 0. The query mod 2 is not 0. Then we want to return false. That's another interesting case. Now we need to come up with the recursive case. So how do we pass this information on and get it back? What does that line look like? We're one line away from being done. Take a minute, talk to the people next to you, see if you can come up with it.
Just what the recursive case is, and just return. I don't clear, but it's. Yeah, you divide it. They really walked us through what she did. That's like investment stuff. I know. I think it's really that's something that's.
We find it. Who has an answer? Yeah, yeah. That's exactly right. So I'm gonna return this exact same method, power of 2. But we need to pass it something that's different. We need to pass it something that's closer to one of these base cases. We just want to pass it half the value. That's right, a quick tester, because we're done. Let's just say. What is a power of 2 that we can test?
4.
Sure. What is a power, that's something that is not a power of 2 that might be tricky to determine if it's a power of 2?
36.
36, that's a great answer, because it's gonna divide 36 into 18 into 9, and then it should run into an issue. Great. So we expect to see true and then false. Which we do. Let's run through these examples and see exactly what's happening. So for the first one, for 4, we're passing in 4 as our query. Is query 1? No. Is query mod 2 not 0? No. So we're going to return power of 2 of query divided by 2. Unfortunately, we don't have an answer to that. So we're going to have to duplicate this process, put this process on hold, move to the person in front of us, and from their perspective, continue this work. 4 divided by 2 is 2, and so query is 2 from that person's perspective. Is query 1? No. Is query mod 2 not 0? No. So we're going to have to call power of 2 for query divided by 2. Since we don't have an answer to that, we're going to put this on pause. So now we have 2 of these instances on pause, and we move to the next person in line. Coming in, we have 2 divided by 2 is 1. So query is 1. Is query 1? Yes. So we return true from that person's perspective, and now we're just playing a game of telephone all the way back down the line. There's no additional work to do. We're just returning whatever the person in front of us said. If the person in front of us said true, we're also going to turn back and say true. So that just propagates back through all the way to the end where we report it, where we print it out. For 36, on the other hand, it's going to look very similar. The last person says no. Query is 36. Is it 1? No. Is mod 2 not 0? No. So we put it on pause. Take 36 divided by 2, 18. Move ahead to the next one. Do exactly the same thing. 18 divided by 2 is 9. Move on to the next one. But now we get caught in this if, because 9 mod 2 is 1, not 0. So we return false immediately when we see that 9, because it is odd. So all the way propagating back through this chain of calls is false, 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 false. And we return that and print it here. So this is a way to think about whether a number is a power of 2 recursively. Yeah, that is something we should probably handle, huh? If we test 0 as a power of 2, is 0 technically a power of 2? Is 2 to the something 0? Let's say that it is false. So if we can say query is 0, or query mod 2 is 0, we can return false. And that will prevent that Stack Overflow exception because what's happening if we can recreate that Stack Overflow exception without that query equals 0? We basically are going to say, is query 1? No. Is query mod 2 not 0? No. 0 divided by 2 is 0 remainder 0, so that's not going to be true. We return power of 2 of 0 divided by 2, which is 0. You can see that that's the exact same problem that we just tried to solve. So this is the equivalent of an infinite loop in a recursive world where we're asking the person in front of us to solve exactly the same problem that we had to solve. So they're going to have to ask the person in front of them to solve the exact same problem, who asks the person in front of them the exact same problem. If we only have a limited number of people to solve this problem, say about 40, then we run out of people. If we run out of people, we get the Stack Overflow exception. So great catch. We should probably include a query equals 0 to return false there. Questions on this example? Confusions on this example? Should I draw this out in more detail? Time to check in. How do we feel about the problem? Thumbs feel good, feel mid. Don't really understand what's going on, and that's okay.
I'm just wondering, can we like somehow just plug an integer in there to count up by 1 for every single time you run power of 2?
Yes, so we're actually going to talk about that when I talk about how to make this more efficient. Java actually can't make this more efficient, which is very annoying. But in some other languages, the way that you structure your recursion can actually allow you to calculate more complicated values. So granted, ints can't store values that are larger than 2 to the 40th. But if we wanted to figure out powers of 2 that were larger than 2 to the 40th, we would have to do something more clever. And I think you're on the right track there, figuring out how to do that. You carry the answer along with you so that you don't need to return the answer from whence it came. By the time it reaches the front of the line, the person at the front of the line knows the answer. All right, ready for our next example? Have we seen the Fibonacci sequence before? Yes, it comes up over and over and over. So we are going to do a recursive Fibonacci, but we should, just as before, start with an iterative version and see if we can improve on the length of that iterative version. So my challenge to you is that we're going to write we're going to write a Fibonacci iterative. We're passing in a single value, so something like the 5th Fibonacci number or the 10th Fibonacci number. So we want to start out, we're going to say the value of the first Fibonacci number is 0, the value of the second Fibonacci number is 1, and then the value of every successive Fibonacci number are the last two, the sum of the last two Fibonacci numbers. So 0 plus 1 is 1, that is the next Fibonacci number. But I should say the 0th Fibonacci number is 0. So let me draw that out real quick. So we have the 0th Fibonacci number is 0, and the first Fibonacci number is 1. So now the second Fibonacci number is the sum of these last two. The third Fibonacci number is the sum of these last two. The fourth Fibonacci number, the sum of these last two. The fifth Fibonacci number, the sum of these last two. This process continues forever. So go ahead and write an iterative version of this that uses a loop. Given that we pass in a value, what is the nth Fibonacci number? I'm going to start out with this. Since we know that these are hard-coded. And go ahead and go from there, see if you can come up with a response. Feel free to talk to your neighbors, pair program this, work it through. We have about 5 minutes, see if we can get this done by the end of class. Deal with your edge cases for you. Anyone come up with an answer? That was just a little bit too little time, and that is perfectly okay. But we are out of time for the day already, somehow. My task for you over the next 24 hours, 23 hours is to finish this off, see if you can finish this off. And if you can finish this off, think about it recursively and see if you can come up with a recursive solution to this problem to at least get started with it. This is very good practice for thinking recursively, as well as just solving some problems. So we'll come back and solve this together at the start of tomorrow's class, but the more work you put into it before then, the more you'll get out of it. So I'll see you tomorrow for that, and I have office hours starting now for the next couple hours.